Exponents are not rocket science. Just as you can get used to spelling long or difficult words in English or in any other language, so can you get used to writing numbers in their exponential format. It's really no different. Now, in this video, we're going to go over positive and negative exponents and scientific notation as well, in that order. But first off, the exponents and numbers in an exponential format is still a number. This number here is 36. Okay? In an exponential format, it's written this way with a 6 and a 2, and I said 36, but there is no digit 3 anywhere to be seen. In an exponential format, there is a number, a bigger number, base, and a smaller number in the upper right hand corner, the exponent number. And just as that is 36 in its standard format, that's also 36 in its exponential format, and if you like Roman numerals, that's also 36. Just as anything else, it's still the same one concept of the amount 36. Whether you spell it this way or this way or this way, it's still 36. Now, this concept of 36, or this concept of the exponential notation, is based on multiplication. And where the multiplication is in this one is that number, the little number 2, the exponent number, shows you how many times the base number is multiplied by itself, not by 2. Because 6 by 2 is 12. This is not 12. This is 36. So, in other words, there is the base number and it's multiplied by itself. So you write down the base number 2 times. The exponent shows you that you write down the base number 2 times and you multiply it by itself. Now that center dot is one way to write multiplication, and on the sidebar here I've got some other ways to write multiplication. Just any random numbers. You have an x to write multiplication with, 2 times 3 or 2 by 3. A center dot, 4 times 5. You can have brackets for multiplication, just like base times height. And sometimes you have nothing between two amounts. That's mass times the speed of light squared, but that's another story. There is a multiplication there. It's not indicated by anything in writing, but it's not only implied, it's really explicit. That's one way to write multiplication. So that's 4 ways there, and here is the 5th way. That's based on multiplication. And whether you write, like I said, 9 times 3 or 6 times 6 or 6 times 6 this way, it's still 36. Okay? The same one number. So that's what these exponents are, and that's how they basically work. Now, negative exponents are coming up, and I'm going to write on this sheet numbers in 3 columns. This will be the column for an exponential format. I'm just going to write exponential form of the same number. It's going to be the same number from line to line to line. Okay? Here it's going to be a multiplication, or an expanded form based on standard multiplication, and I'm going to use a center dot for this multiplication. So this is the multiplicative form, and here I'm just going to write the same number in just standard Arabic numerals. Okay, so I'm just going to go Arabic numerals. Numeral. Okay, does it fit the screen? Kinda does. Okay, so let's start here. 2 to the power of 2, or 2 squared, 2 to the power of 3, or 2 cubed, 2 to the power of 4, and 2 to the power of 5. So these are the powers of 2. If I write them in multiplicative expanded form, it's fairly straightforward. You take the base and you write it down 2 times, and you multiply them together. Oh, sorry about that smear. And of course in Arabic numeral it's just 4. This is 4, this is 4, 2 by 2, and this is 4. Either which way you look at it, it's still the same one concept. The next one, 2 cubed or 2 to the power of 3, can be written as 2 by 2 by 2, like so, and of course it's 8. So you can write 8 this way, or this way. It's still the same 8. 2 to the power of 4, you take the base 2 and you write it down 4 times, multiplying by itself each way or each time, and that's of course 16. And the last one, 2 is written down 5 times because 5 is the exponent number there, and of course it's the same number as 32. So I chose the powers of 2, or the multiples of 2, or the multiples of 2 to demonstrate this equivalency between one form, another form, and the third form, because you have all seen 4 gigabytes, 8 gigabyte, 16 gigabyte, and 32 gigabyte items in computing and technology. By no coincidence, computing science is based on multiples of 2. Okay? Negative exponents are coming up, the next item on our menu list here. And I know this is a long video, so thank you for watching and listening. You can just fast forward whatever to the part that you need to fill in your missing link in your chain of thought. Look at the exponent number here. We're going to the negative numbers. 5, 4, 3, 2. If I write down the base there, what's going to be the next exponent number on it? If we keep going with the same pattern, subtracting 1 each time. Subtract 1, subtract 1, 2 minus 1. The next exponent number will be, of course, 2 to the power of 1. The next will be 2 to the power of, by subtracting 1 from the previous, 1 minus 1 is 0. Yes, there is 2 to the power of 0. The next one will be subtracting 1 again, 2 to the power of negative 1, subtract 1 again, 2 to the power of negative 2, and the last one will be 2 to the power of negative 3. That fits the sheet here. Now back to the multiplication here. Like I said, for example, 2 to the power of 3 means that you take 2 and you write it down 3 times, because 3 is the exponent number, and this many times the base is multiplied by itself. So when we get to 2 to the power of 1, unfortunately this explanation with multiplicative expansion doesn't work out. I cannot write down the base one. I can write down the base once, but I can't multiply it by itself once. There's no such thing. It doesn't work. Especially it doesn't work with 0. The 0th power of 2, I can't write down the base 2 and multiply it 0 times. Not by 0, multiply it by 0 times, or write down the base 2 and multiply it by itself negative 3 times. It's not working that way. So there's nothing here for multiplication. I can't model it with multiplication. Alright. However, the numbers exist. They just don't work out with this explanation. Okay? This number exists, that number exists, and that number exists, and it has a normal value. And I'm gonna show you how that value is generated, because there's another pattern here. Alright, so I hope that makes sense, that there's no this multiplication model here ends about there. And we have another pattern here when the number is written down in standard Arabic numerals here. To get from 32 to 16, what do you have to do? Other than subtract 16, because that won't work repeatedly. To get from 32 to 16, I have to divide by 2. To get from 16 to 8, you have to divide 16 by 2 by the base. To get from 8 to 4, you have to again divide by the base 2. 8 divided by 2 is 4. So the next number will be, if we continue with the pattern here and divide 8 by the base, is 8 divided by 2, 4 divided by 2 is 2. So 2 to the power of 1 is 2. This number is the same as that number, whether you write it this way or that way. It's the same one concept. Next one will be, same pattern continues. 2 divided by 2 is 1. 2 to the power of 0 is 1. Okay. The next one will be, same pattern. What's 1 divided by 2? I'm just gonna go 1 over 2, or of course you can write it in a decimal number, 0.5. Whether you write it in a fraction or in a decimal, you say half. It's the same amount. Whether you write it as a decimal or as a fraction or as an exponent here or an exponential form, these three are still the same one amount, half. 2 to the power of negative 1, half 1 over 2, or half 0.5. It's the same thing. The next number will be, of course, generated by dividing the previous one by the base. So what's half of a half? It is a quarter. Of course you can write it in a decimal this way. And 2 to the power of negative 2 is the same as a quarter. That's the same number. The next one and the last one on this sheet is, what is half of a quarter? Half of a quarter is an eighth, and you can write it then as 0.125, or 1 over 8, or 2 to the power of negative 3. It's the same number, 1/8. Do notice that we have a pattern here. 1 over 2, 1 over 4, 1 over 8, 2, 4, 8. So the next number down here on the list, where I don't have any paper, will be 2 to the power of negative 4, and it's going to be 1 over 16. 2 to the power of negative 5 will be 1 over 32, 1 over 64, 1 over 128. And not coincidentally, on a tape measure, you have halves, quarters, an eighth of an inch, 1/16th, 1/32nd, 1/64th, 1/128th of an inch, and it keeps going, because the fractions of an inch is also based on the concept of multiples of 2 or fractions of 2. Okay, so I wanted to show you this here with 2 being the base, because most people can relate to computing and measurement. And the same continues with 10 being the base. I'm going to repeat the same 3 columns here: the expanded form, the exponential form, the multiplicative expanded form, and I'm going to calculate here a result and just write it in normal Arabic numbers. And powers of 10. Powers of 10 are necessary for scientific notation, because the powers of 10 is the basis for the scientific notation. So very quickly, 10 squared, 10 cubed, that's a 3, and 10 to the power of 4. In a multiplicative expanded form here, this means that you write down the base, 10, 2 times, and you multiply it by itself. And of course 10 by 10 is 100. It's not 20, it's not 10 by 2, it's 10 by 10. 10 to the power of 3, and of course will be the base written down 3 times and multiplied by itself each way. Of course the answer is 1000, and 10 to the power of 4 will be 10 by 10 by 10 by 10. Of course it's 10 1000. The same patterns work as previously. Look at the exponent numbers 4, 3, 2, subtracting 1 each time as we're going down. The next exponent number will be 10 to the power of 1, because we're subtracting 1. The next will be 10 to the power of 0, 10 to the power of negative 1, 10 to the power of negative 2, and 10 to the power of minus 3. Likewise, as before, the multiples of the expanded form explanation ends here. I cannot write down 10 negative 2 times. That would be holes in the paper in the shape of 10, or and it doesn't work that way. So there is nothing here for multiplication. Nobody can, I can't explain the exponents of 1, 0, negative 1, 2, and 3 and model it with multiplication. It cannot be done, okay? However, 10 to the power of negative 2 is still a number, and we're going to get to it the same way as we worked our way through with the multiples of 2. So to get from 10,000 to 1,000, we can do this by dividing by 10, dividing by the base. To get from 1,000 to 100, we need to again divide by the base. And to get from 100 to the next result, for 10 to the power of 1 would be, it's 10 because we're still dividing by the base. Same for the next step. 10 divided by 10 is 1. So 10 to the power of 0 is 1. And not coincidentally, is 10 to the power of 0 is also 1. Sorry, 2 to the power of 0 is also 1, just as 10 to the power of 0 is also 1. It is a logical necessity. All of these patterns will be 1 at this point, at the 0th power. Continuing the pattern, we divide the previous one with the base, and 1 divided by 10 is 1/10 that way or 1/10 that way, but it's decimal fraction or exponential format, it's the same idea. Further divide by 10, 1/10 divided by 10th, 10 is 100th this way or 100th that way, and the last division by 10 is producing 1,000th. A tenth of 100 is 1,000th, and there you have it in decimal, fraction, and exponential form. So these are the powers of 10. Your money, your currency, is based on multiples of 10. You have dimes, you have cents, you have dollars, and you have multiples. You have a tens column, a ones column, hundreds column, a thousands column, okay? So most people can relate to this one, especially in the English-speaking countries. On the last page here, I'm going to explain scientific notation using the multiples of 10 or the exponents of 10. For example, 500, the number 500 can be written this way, or it can be written this way. Both of these mean 500. How do I know this one is 500? 10 to the power of 2 is 10 times 10. 10 times 10 is 100. And we still have there times 5. So it's 5 to the power of 5 times 10 to the power of 2 is 5 times 10 by 10. 5 times 100, it's 500. Another number, just to get you another example with a decimal here at the beginning. For example, I don't know, 4.7 times 10 to the power of, how about a little adventure, 4, would be what number? Same line of thinking is going to apply. 10 to the power of 4 is, you write down 10 4 times, multiplying by itself each time. So 10 by 10 by 10 by 10, that's 10,000, or a 1 followed by 4 zeros there, 4 zeros there. And to calculate this number, or to come up with this number in a standard format, you write down the 4.7 and you move the decimal dot over 4 spots going that way, because it's 10,000 has so many zeros running this way from left to right. So you start there, grab the decimal dot, drag it over once, twice, thrice, and the 4th time, and the decimal dot rests there, and then fill it in with zeros there. The number is 47,000. So this number is 47,000, this number is 47,000, either which way you look at it. Scientific format, standard format. Alright, why would anybody bother with scientific format when this one is so much simpler and cleaner? Yeah, with small numbers it is. Looky here. How about 8.2 times 10 to the power of, how about 12? I hope that fits the paper. 10 to the power of 12 is 10 by 10 by 10 by 10 by 10. Let me see, 1, 2, 3, 4, 5, 6 by 10 by 10 by 10 by 10 by 10 by 10. In other words, 1 is followed by 12 zeros. So, to get this number in its standard format, you would need to go, it is 8.2, and you move the decimal dot 12 spots over, going that way. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Decimal dot stops there and rests there, and fill it in with extra zeros, just like so. To name this number, and this is another advantage of the scientific notation. First off, scientific notation is a lot shorter than this. Another point is, how do you just name this number? Let me see, there's 3 zeros there for the thousands, 3 zeros there, so those would be your millions. The next 3 is there, and the next 3 is there. So here is where differences begin. After the millions, whether you're using the short scale or long scale, numbers are named differently. So if you're using the long scale, you have millions, milliards, billions, billiards, trillions, trilliards. If you're using the short scale, it's millions, billions, trillions. So this number would be 8 quadrillion, 2 trillion. And that's the end of it. That's it. That's the name of the number. 8 quadrillion, 2 trillion. But if you're using the long scale, its name is going to be different. So, to avoid international differences and World War III over how we name this number, we'll just go with, and the scientific community just goes with, 8.2 times 10 to the power of 12, end of story. I'm going to repeat the same with negative exponents so you see how it works, just for good measure. Oh, ran out of paper there. I'm just going to flip it over. And how about a negative exponent number, for example? The number for the thermal, what kind of coefficient is that? Linear, yeah, the linear expansion. Linear expansion of aluminium or aluminum, depending on where you're listening and watching, is 23 times 10 to the power of 6. That's the coefficient of linear thermal expansion for aluminum. Okay, name that number. What number is that? Okay, to get this unpackaged, a negative exponent means that it's a 1 over, and then 10 to the power of positive 6 means that you write down 10 by 10 by 10 by 10 by 10. So 1, 2, 3, 4, 5. You write down the base 6 times, and that negative exponent means that it's 1 over. So that's 1 over, you got 6 zeros there, 1 over a million, or 1 over a million there. There's your, sorry, not enough zeros there. Now you have 6 zeros there. A little bit ugly there, but that's 6 zeros, okay? 1 over a million, that's fraction format. That doesn't help a lot. Oops. Doesn't help a lot. We need decimal, so it would be 3, 4, 5, 6. Okay, so that would be your tenths, the hundreds, the thousands, 10,000, 100,000, millionth place value. So that's 1 millionth in decimal format. So to make sense out of this number, you write down the 23. 23 is the same as 23.0, right? So I'm just gonna do an invisible 0 that's always there. 23.0. And then because we're going this way with the decimal dot, I'm gonna start here and move it over 6 spots, because that's the exponent number, and that negative means we're moving from right to left. So that's 6 jumps. 1, 2, 3, 4, 5, 6, and that's where the decimal dot rests. And fill it in with extra zeros. There you have it, 0.000023, or 23 millionth. Either which way, that's the name of the number, whether it's this way or that way. Now, and this one is alright, 23 millionth, but what do you do with a number such as the elementary charge of a single electron? That number is 1.6 times 10 to the power of negative 19. This is in scientific notation. Good luck naming it. I can write it out in decimal format, and this is how it's going to look like. You write down the 1.6 somewhere there, and we're going to move over 19 spots from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That's where the decimal dot stops, and just fill it in with zeros, real casual here. There, I hope I have all of the zeros that I need, so let's count them quick. 3, 6, 9, 12, 15, 18, and there's the 19th. Excellent. So this is why they use scientific format. Again, I'm not even gonna attempt naming this number, especially not on a short scale. Maybe on a long scale it's in the trillionth range or whatever it is. It's a lot shorter, and it's crystal clear what number it is when it's in a scientific format instead of a standard format. So it's been a long video. Thank you for watching, and I hope this scientific notation and exponents and everything will make sense. Once you have a clue and once it makes sense, then we can get started with doing actual math, because this is just going from one format to another format. Math starts from hereafter with adding, subtracting, multiplying and dividing. So those will be separate videos.